how does anyone build a tower just 57 feet wide and 1,428 feet tall? The proportions barely seem plausible. A standard New York taxi is roughly as wide as this entire skyscraper. Hundreds of feet up, an 800-ton counterweight sways constantly to keep the structure from twisting in the wind. Several floors were deliberately left open, so gusts pass straight through rather than push against the building. Look down from the upper levels, and there's nothing between you and the Manhattan pavement far below. 200 steel anchors are drilled deep into bedrock beneath the site, not to hold the tower up, but to pull it down against the force of the wind. The project took 7 years, built into a narrow gap between two existing buildings, and stands today as the thinnest skyscraper on Earth. Every neighboring site had a clear lot to build on. This one didn't. Beside it stood Steinway Hall, a landmark building nearly a century old, where Glenn Gould gave his final public concert. Preservation rules meant not one stone of it could be touched. That left only a 57-foot strip of buildable land, and from that sliver rose the world's thinnest tower. With a height-to-width ratio near 124, wind doesn't just push a building like this, it tries to flip it over. 57th Street itself acts like a wind tunnel between two avenues, and the tower sits right in that channel. Anchors hold the base down, sheer walls carry the load up, and a tuned mass damper near the top kills the sway. To make it possible at all, developers paid roughly $131 million just for air rights above a neighboring roof, a deal only New York real estate makes necessary. Excavation began just 12 inches from the fragile, century-old foundation next door. Beneath Midtown lies solid bedrock, and crews here had to drill through some 30 feet of it, clearing everything to within a single foot of the historic limestone facade. Steinway Hall's old footings extended directly into the new foundation zone, so engineers threaded new concrete piers between them, permanently locking old and new foundations together. Heavy equipment worked within a 57-foot site, inches from a fragile landmark. Drill rigs bored 100 feet into solid Manhattan schist, roughly 10 stories below street level, lowering 100-foot rebar cages into place before pouring concrete. Because the footprint was so tight, each pier had to carry the load of about 20 ordinary ones. The ground anchors brought their own challenges. Each consists of roughly 100 feet of steel tendon bonded into bedrock with epoxy, effectively becoming a permanent part of the rock itself. At one point, drilling struck a fracture, throwing an anchor out of alignment and preventing the grout from setting. The fix was to seal the fracture with pressurized grout, let it cure, then re-drill through the sealed rock and start again. In total, 200 anchors were installed, each rated to resist about 600 kips, pinning the tower to bedrock before a single floor above ground existed. When wind tries to lift or rotate the building, the anchors and the rock beneath them resist it. The entire system in one sentence. Above ground, the core walls run just 36 inches thick on a tower 57 feet wide and 1,128 feet tall, the thinnest shear walls ever used at this height. The concrete is rated at 14,000 psi, about 4 times normal strength, the only mix strong enough for a tower this narrow. The 2 shear walls alone required roughly 5.5 million feet of rebar, enough to circle Manhattan some 200 times. Construction moved at about 1 floor every 5 days, with self-climbing formwork rising alongside the cured concrete. Wall thickness tapers from 36 inches at the base to 16 inches near the top, since wind-driven bending forces are strongest lowest down. Concrete was placed in 12-inch lifts, vibrated internally every 18 inches, with 0 voids allowed. At one stage, the formwork began cracking under the pressure of the fresh 14,000 psi mix. Had it failed, the pour would have stopped for good. Emergency tiebacks were welded in within 20 minutes, and the pour resumed exactly where it left off. Structurally, The core plus the two shear walls act as one enormous I-beam, 57 feet across. As the tower rises, the concrete actually gets weaker because wind forces on the upper floors are proportionally smaller. Engineers placed critical outrigger connections at floors 38 and 70, tying the two shear walls into a single system so the building behaves as though it were 180 feet wide instead of 57. One of these connections was built directly above an active piano showroom, with micropile rigs drilling below it, all without disturbing the retail floor. Walk one block north, and the entire 1,000-foot tower disappears behind other buildings, a product of just how thin it really is. Partway up, engineers caught a lean of 0.8 inches at floor 22, a deviation that would compound with every additional floor on a tower this slender. Two corrective pours, each shifted 0.4 inches south, brought the wall back to true by floor 25. Two full floors were left open to let wind pass through the core rather than around it, cutting the sway significantly. By April 2019, the concrete had topped out at floor 85. By then, a visibly thin blade said to be visible from New Jersey. The finished structure came in with just 1.1 inches of total deviation over about 435 meters of height, close to the limit of what's achievable at this width. One especially demanding pour, at floor 36, placed 14,000 PCI concrete 4 meters deep in a single continuous shot. There's no fixing an outrigger wall a second time. With the concrete complete, crews turned to structural steel. In one striking moment, a 200-ton steel truss spun in the wind above the city while 4 ironworkers guided it into place by hand. This steelwork, along with the crown above it, gives the tower its final silhouette. Because 57th Street had no room to stage materials during the day, flatbed trucks delivered oversized steel sections at 3 in the morning. One embed plate, cast 2 years earlier, needed to align precisely with the new outrigger truss, but the bolt holes didn't match. The embed had shifted 0.6 of an inch over those 2 years, with no way to reverse it. So engineers used slotted holes to absorb the offset, torqued each connection to 880 foot-pounds, and accepted it as permanent. Every wind force from the roughly 60 floors above passes through that one truss. Near the top, a spire doubles as a required FAA aviation marker at an exact height and position. Ironworkers bolted its sections together by hand in sub-zero temperatures at 1,200 feet. Inside, the tower packs in 14 elevators despite its narrow footprint, 2 of which open directly into individual apartments with no shared corridor. An 800-ton steel damper sits inside the crown. The exterior is clad in terracotta, 26 custom shapes across 6 colors, every panel individually fired in Germany for this building alone. While nearly every other super tall on this stretch of street is glass, the design team chose terracotta and bronze instead. The clay goes into the kiln gray and emerges golden after firing at roughly 100 degree axes. Each panel hangs from steel clips on aluminum rails fixed to the shear wall, carrying no structural load of its own. The building's 7 setbacks required 7 entirely new edge profiles that didn't exist in any manufacturer's catalog, each requiring a new extrusion die, some 500 sample panels, and tolerances held to 0.5 millimeter. With no room for scaffolding on a site this narrow, crews hung the terracotta from the building's own window washing track, securing each panel with a permanent quarter-turn lock. The setbacks themselves were designed to make the tower visually dissolve as it climbs into the sky. Bronze panels between the terracotta sections were hand-finished at a Brooklyn foundry, specifically for this project. The north face, by contrast, is left completely flat with no setbacks, one unbroken plane from street to sky. At the corners, the terracotta curves rather than miters, each curved piece individually designed and fired. During construction, engineers found galvanic corrosion developing at floor 45, where bronze and aluminum were in direct contact and reacting with one another. Neoprene washers installed at every contact point broke the circuit and stopped it. Floor-to-ceiling glass on the north and south faces frames Central Park on one side and the city on the other, while one mechanical floor was left uncladded on those faces entirely, letting wind pass straight through. The terracotta fins along the edges are designed to make the tower look even thinner through shadow. Wrapping the concrete in a terracotta and glass skin created a new problem: sealing the building without dangerous pressure buildup. At one point, wind pressure tore a door from a worker's hands on floor 40. The tower functions something like a chimney, with pressure at the top pushing outward on every door. Measured pressure at the upper floors reached about 100 pascals, while doors above floor 60 were only rated for half that. The fix combined 120 pascal rated doors with a lobby pressurization system, restoring normal operation. Separately, a 500-pound glass panel became a dangerous sail at around 700 feet, requiring 3 workers to control it in 35 mph winds, capable of exerting some 800 pounds of lateral force on a panel that size. As a result, glass installation was restricted to a short morning window, 6 to 9 a.m., confirmed safe by a meteorologist each time, no exceptions. Plumbing brought its own failures. A pipe at floor 70 burst outright. Pumping water 700 feet up generates pressure standard piping can't handle. The pump was pushing roughly 300 psi against pipe rated for only 140, and it failed.
Engineers split the system into 6 pressure zones. A booster pump is placed roughly every 14 floors. This keeps every pump under about 200 psi.
The elevators faced a parallel problem. One rail developed a 12-millimeter bow from the building's sway, risking derailment for a car moving at 20 feet per second. Spring-loaded guides now absorb up to 25 millimeters of rail deviation, backed by active monitoring. In a building that sways this much, rigid rails simply aren't an option. Even the tower crane became a problem. Traditional crane jumping needs more lateral room than a 57-foot building allows, leaving the crane stranded on the roof once construction topped out. The solution was to bring in a smaller crane to dismantle the original section by section down the building's east face until the last piece reached the street and 57th Street reopened. A swimming pool on floor 17 posed an unexpected structural risk, behaving like a 75-foot wave machine.
If its natural sloshing frequency ever matched the building's own sway, the resulting resonance could damage the structural floor beneath it.
The pool's roughly 6.8-second slosh period sat dangerously close to the tower's 7.5-second sway cycle, producing standing waves. A perforated steel baffle cut wave height from about 3 feet to 4 inches, resolving the risk. Separately, a 2-ton marble bathtub had to be hoisted some 800 feet up and guided through an open exterior panel by 2 workers, since it was too large for any elevator. Interior work preserved history alongside the new construction. An ornamental dome was removed, stripped, re-gilded, and reinstalled, revealing century-old plasterwork hidden beneath a 1960s ceiling. The lobby floor is base-isolated, so the tower and its historic neighbor can move independently in a storm while the connecting floor stays level. Roughly 12 tons of cantilevered concrete extend 6 feet over 57th Street, held by 4 post-tensioned rods. The rooftop pool's waterline was surveyed to the centimeter, so it aligns visually with the Central Park tree canopy below.
Our motion sensors are highly precise. They register lateral acceleration as low as 5 milligravities at 20 feet per second.
And roughly 10,000 sensors throughout the building continuously track strain, temperature, and deflection every 30 seconds, day and night. The tuned mass damper sits still under normal conditions but activates whenever a major storm approaches. In significant wind events, the building has swayed as much as 30 inches at the top, with the damper absorbing about 12 inches of that motion in real time. During a January 2021 storm with 78 mph gusts, the The tower swung roughly 8 inches at floor 75 as the damper moved to counter it. At the foundation, wind loads can generate up to 4,000 kips of uplift, which the anchor system is built specifically to resist. Certain wind speeds can even set the structure vibrating like a tuning fork, a frequency the damper is calibrated to counteract. From as far as the George Washington Bridge, some 9 miles away, this needle-thin tower remains visible against the skyline, a striking demonstration of how far modern structural engineering has been pushed.